Hello there and welcome to Science for Sleep. Tonight we're exploring something quietly unsettling about the universe we think we understand. Gravity, that familiar force pulling you gently into your chair right now, holds secrets that our most elegant equations simply cannot explain. There's a growing mystery in physics, a paradox where our mathematical descriptions of gravity keep failing when we look closely at how galaxies actually move, how space itself seems to bend and stretch in ways we didn't predict. It's not that gravity is broken, but rather that something fundamental about reality might be more complex, more layered than we've imagined. Tonight, we'll move slowly through this puzzle together, examining why the force that keeps your feet on the ground becomes mysteriously elusive when we try to understand it on cosmic scales. If this gentle exploration through one of science's deepest questions helps you find calm or curiosity, your quiet support means everything. Let's begin this patient journey into gravity's hidden mysteries. Hello there, and welcome to Science for Sleep, where tonight we explore something quietly extraordinary about the universe we think we understand. Can you feel it right now, that invisible force gently pulling you deeper into your chair or bed, keeping your feet connected to the ground beneath you? This is gravity, perhaps the most familiar yet mysterious force in existence. And tonight we'll discover why this seemingly simple phenomenon has become one of physics' most perplexing puzzles. Whether you're settling in for the evening, finding a moment of calm in your day, or simply curious about the cosmos that surrounds us, you've arrived at the perfect place for a gentle journey through one of science's greatest unsolved mysteries. If this peaceful exploration through the hidden complexities of gravity brings you comfort, knowledge, or simply a few minutes of tranquil learning, your quiet support through a gentle subscription, or sharing your thoughts means everything to our small community of cosmic explorers. Tonight we'll move slowly and patiently through ideas that challenge everything we thought we knew about the force that shapes galaxies, bends space itself, and somehow fails our most elegant equations when we need them most. There's no hurry in our exploration, no pressure to grasp every concept immediately, just an invitation to drift alongside these fascinating questions that have puzzled brilliant minds for decades. What if the force that seems so predictable, so reliable in dropping an apple or keeping planets in their orbits, actually behaves in ways that our mathematics simply cannot explain when we venture beyond our familiar solar system? This gentle contradiction between the gravity we know and the gravity we observe lies at the heart of modern cosmology's greatest challenge, where the most successful theories in human history encounter their most profound limitations. As we begin this unhurried journey together, let yourself settle into the rhythm of discovery, knowing that some of the universe's most beautiful mysteries reveal themselves not through rushing toward answers, but through the patient contemplation of questions that have no easy solutions. The gravity pulling you toward Earth right now operates according to laws we've understood for centuries. Yet this same force somehow produces effects across cosmic distances that require us to imagine either vast amounts of invisible matter or fundamental changes to physics itself. What makes an apple fall from a tree with such precise, predictable motion that we can calculate exactly when and where it will land? This simple question sparked Isaac Newton's revolutionary understanding of gravity over 3 centuries ago, creating mathematical descriptions so elegant and reliable that they've guided everything from architecture to space exploration with remarkable success. When Newton watched that famous apple descend, he recognized something profound about the universe. The same force pulling fruit earthward also keeps our moon circling overhead, guides planets in their eternal dance around the sun, and governs the rise and fall of ocean tides with clockwork precision. His equations became humanity's first universal language for describing motion, working flawlessly, whether predicting the trajectory of a thrown baseball, calculating the orbit of a satellite, or determining the gravitational pull between any two objects in our solar system. These mathematical relationships have proven so dependable that engineers use them to launch spacecraft across billions of miles with pinpoint accuracy. Architects rely on them to construct towering buildings that won't topple, and physicists apply them to understand everything from the formation of planets to the behavior of binary star systems. For 300 years, Newton's inverse square law has provided comfort through its consistency, describing how gravitational force decreases with distance in a pattern so reliable that we rarely question its universal applicability. Every falling leaf, every orbiting comet, every rising tide confirms what Newton discovered. Gravity operates according to simple, beautiful mathematics that connect the motion of celestial bodies with the dropping of objects here on Earth. The elegance lies in gravity's apparent simplicity, requiring only mass and distance to predict how objects will move through space, creating a cosmic choreography that unfolds with mathematical precision, whether we're observing the swing of a pendulum or the elliptical path of Mars around our Sun. This predictability has made gravity feel solved, understood, domesticated by human intellect into neat equations that work so consistently, we've built our entire understanding of physics upon their foundation. When we calculate the gravitational attraction between Earth and Moon, Newton's mathematics perfectly explain why our satellite maintains its stable orbit, neither flying away into space nor crashing into our planet's surface. Similarly, these same equations accurately predict the complex gravitational interactions within our solar system, explaining how Jupiter's massive presence influences asteroid trajectories, how Saturn's rings maintain their structure, and how tiny Pluto follows its distant, elongated orbit with mechanical regularity. The mathematics work beautifully for binary star systems, where two massive objects spiral around their common centre of gravity in patterns that unfold exactly as Newton's equations predict, sometimes for millions of years without deviation. Even more remarkably, these 3-century-old formulas successfully guided the Voyager spacecraft past multiple planets, using gravitational slingshots to accelerate through the outer solar system with trajectories calculated decades in advance. But here's where our story takes an unexpected turn. What happens when we point our telescopes beyond the comfortable boundaries of our solar neighbourhood and attempt to apply these trusted equations to larger cosmic structures? Something strange begins to emerge as we venture farther from home, examining gravitational behaviour in systems vastly larger than anything Newton could have imagined. The same mathematical relationships that work perfectly for everything within our solar system somehow begin producing predictions that don't match what we observe when we study galaxies, those enormous islands of stars scattered throughout the universe like distant lighthouses in cosmic darkness. These galactic systems, containing hundreds of billions of stars bound together by gravity, should behave according to the same fundamental rules that govern planets orbiting our Sun. Yet careful observations reveal something unexpected, something that challenges our most basic assumptions about how gravity operates on the largest scales imaginable. What happens when the most reliable force in the universe begins whispering secrets that our best mathematics cannot decipher? As astronomers in the early 20th century extended their observations beyond our familiar solar neighbourhood, they encountered the first gentle hints that something profound might be amiss with our understanding of gravity's behaviour across cosmic distances. The transition from studying nearby planetary motions to examining distant stellar systems seemed straightforward initially, like stepping from a well-lit room into twilight where familiar objects gradually reveal unfamiliar shadows. Early telescopic surveys of star clusters and nearby galaxies produced measurements that mostly aligned with expectations, yet occasionally yielded results that didn't quite match the precise predictions derived from Newton's trusted equations. These discrepancies weren't dramatic failures or obvious contradictions, but rather subtle misalignments between theory and observation, like finding that a perfectly tuned piano produces notes that are almost, but not exactly, the frequencies you expect. In the 1930s, a brilliant Swiss astronomer named Fritz Zwicky made observations that would quietly revolutionize our understanding of the cosmos, though few recognized the implications at the time. Working at the Mount Wilson Observatory in California, Zwicky focused his attention on the Coma Cluster, a collection of over 1,000 galaxies bound together by their mutual gravitational attraction, located roughly 300 million light-years from Earth. Using the Doppler effect to measure how fast individual galaxies within this cluster were moving, Zwicky discovered something puzzling. These massive stellar cities were racing around their cluster's centre at velocities far exceeding what Newton's gravitational mathematics predicted they should maintain. According to established physics, galaxies moving at such tremendous speeds should have escaped their cluster long ago, flung into the cosmic void by centrifugal forces that overwhelm the gravitational attraction holding the system together. Yet there they were, somehow remaining gravitationally bound despite their inexplicably rapid motions, like runners sprinting around a track at speeds that should send them flying off into space. Zwicky's calculations suggested that the visible matter within the cluster provided only about 1/10 the gravitational force necessary to keep these speeding galaxies from dispersing across the universe, creating a profound puzzle that would haunt astronomy for decades to come. This wasn't the kind of observational error that could be dismissed easily, nor was it a measurement so far outside expectations that it obviously indicated equipment malfunction or calculation mistakes. Instead, Zwicky had uncovered a quiet but persistent discrepancy between what gravity should accomplish according to our best theoretical understanding and what actually seemed to be occurring in this distant corner of the universe. The unease wasn't immediate or dramatic, but rather grew slowly as other astronomers confirmed similar observations in different galaxy clusters, revealing a pattern of gravitational behavior that consistently exceeded theoretical predictions. These early hints of cosmic mystery created a gentle but persistent tension within the astronomical community, where scientists found themselves confronting the uncomfortable possibility that their most fundamental assumptions about gravity might be incomplete or incorrect. The feeling resembled discovering that a trusted friend had been keeping important secrets, not through deception, but because they possessed knowledge that exceeded your ability to understand or accept. Other observers began noticing similar anomalies in different cosmic environments, finding that double star systems occasionally exhibited orbital behaviors that deviated slightly from Newtonian predictions, and that some nearby galaxies displayed rotational characteristics that didn't align perfectly with calculations based on their visible stellar content. These weren't catastrophic failures of physics, but rather accumulated evidence that something subtle yet significant was occurring in gravitational interactions across large distances, something that our equations couldn't quite capture, despite their remarkable success in describing planetary motions and terrestrial phenomena. The mystery deepened as improved telescopes and more sophisticated measuring techniques confirmed these initial observations, while revealing additional anomalies in even more distant cosmic structures, creating a growing sense that the universe might be more complex and surprising than our mathematical model suggested, setting the stage for discoveries that would challenge our most basic assumptions about the nature of reality itself. How can careful measurements of starlight lead to the complete overthrow of humanity's understanding of cosmic architecture? In the 1970s, an extraordinary astronomer named Vera Rubin embarked on what seemed like routine observations of spiral galaxies. Yet her patient, meticulous work would ultimately reveal one of the most profound mysteries in modern physics. Rubin spent countless nights at observatories carefully measuring the velocities of stars within distant galaxies using spectroscopy, a technique that analyzes how light shifts in frequency when objects move toward or away from Earth. Her methodology was straightforward: point sophisticated telescopes at spiral galaxies, capture the light from individual stars at various distances from each galaxy's center, then analyze how that starlight revealed the orbital speeds of stellar inhabitants throughout these cosmic whirlpools. The expectations were clear and seemingly unshakable, based on centuries of successful gravitational theory and direct observations within our own solar system. Just as planets closer to our Sun orbit faster than those farther away, with Mercury racing around its elliptical path while distant Neptune crawls through its enormous orbit, astronomers anticipated that stars near galactic centers would move significantly faster than those inhabiting the outer edges of spiral arms. Picture stirring thick soup in a large pot. Your spoon moves fastest near the center where you apply force, while ingredients near the edges barely participate in the circular motion. Similarly, imagine an old vinyl record spinning on a turntable. Points closer to the center complete their circular journey much more quickly than locations near the rim, creating a smooth gradient of velocities from fast inner rotation to slow outer movement. Galactic rotation should follow this same pattern because most of each galaxy's mass concentrates in its bright central bulge, where millions of stars cluster together in a dense, gravitationally dominant core. According to Newton's mathematics and centuries of observational confirmation, this central concentration of matter should control the orbital behavior of stars throughout the galaxy, with gravitational influence weakening predictably as distance increases. Rubin expected to find exactly this relationship: rapid stellar motion near galactic centers tapering off to much slower speeds in the sparse outer regions where starlight grows dim and matter becomes scarce. Instead, her careful measurements revealed something completely unexpected and profoundly troubling for established physics. Stars throughout spiral galaxies maintained nearly constant orbital velocities regardless of their distance from the galactic center, creating flat rotation curves that defied every theoretical prediction. Instead of decreasing smoothly like planetary motions or record player rotation, stellar speeds remained essentially uniform from the bright central regions all the way out to the faint, barely visible edges of galactic disks. This wasn't a subtle deviation or minor discrepancy that might be explained by measurement error or incomplete data. Rather, Rubin had discovered a fundamental breakdown in our understanding of how gravity operates on galactic scales. The implications were staggering because this uniform rotation pattern suggested that either galaxies contained vastly more matter than anyone had imagined, hidden somehow beyond the reach of telescopic detection, or gravitational physics itself required radical revision to accommodate these unexpected observations. Rubin's discovery represented far more than an astronomical curiosity or technical puzzle for specialists. It challenged the very foundations upon which modern cosmology had been constructed. Her flat rotation curves implied that our most basic assumptions about matter, energy, and gravitational interaction might be fundamentally flawed, opening possibilities that would have seemed like science fiction just decades earlier. The beauty and terror of Rubin's work lay in its elegant simplicity. By carefully measuring how fast stars orbit within distant galaxies, she had uncovered evidence that the universe contains either enormous quantities of invisible matter or operates according to gravitational rules completely different from those governing our everyday experience. This single woman's patient observations, conducted night after night with methodical precision, had revealed a cosmic puzzle so profound that it continues to baffle the brightest minds in physics decades later. Her revolutionary discovery would spark an ongoing scientific revolution, forcing astronomers to confront the uncomfortable possibility that visible matter represents only a tiny fraction of the cosmic reality, while the vast majority of the universe consists of something mysterious, undetectable, and utterly unlike anything we had ever encountered before. Why do the most elegant mathematical relationships that perfectly describe our solar system completely fail when applied to the vast stellar cities we call galaxies? To understand this profound breakdown in physics, imagine watching children on a playground carousel where those sitting near the center spin rapidly while kids positioned on the outer edge barely move at all, creating a smooth gradient of velocities that matches exactly what we observe in our own cosmic neighborhood. Mercury blazes around the Sun at nearly 50 kilometers per second, completing its orbit in just 88 Earth days, while distant Neptune crawls along at a leisurely 5 kilometers per second, taking over 160 Earth years to complete a single revolution. This dramatic difference in orbital speeds creates what astronomers call a Keplerian rotation curve, where velocity decreases smoothly with distance from the central gravitational source following mathematical principles that have guided spacecraft navigation and planetary predictions for centuries without ever failing us. The physics behind this behavior seems almost intuitive. Objects closer to a massive central body experience stronger gravitational pull and must move faster to maintain stable circular orbits, while those farther away feel weaker attraction and naturally settle into slower, more leisurely orbital patterns. Think of water swirling down a drain where liquid near the center rushes rapidly toward the opening, while water at the edges barely participates in the circular motion. Or consider how pizza dough behaves when spun by an experienced chef, with the inner portions rotating quickly, while the outer edges lag behind in their angular journey. These everyday examples all demonstrate the same fundamental principle that governs planetary motion. Rotational velocity decreases with distance from the center of attraction, creating predictable patterns that mathematicians can describe with beautiful precision. Galaxies should behave according to these same physical laws, because most of their visible matter concentrates in bright central bulges where millions of ancient stars cluster together, creating gravitational cores that should dominate the orbital dynamics of everything within these cosmic systems. Yet when Vera Rubin and her colleagues measured actual stellar velocities within spiral galaxies, they discovered rotation curves that were completely flat, meaning stars throughout galactic disks maintained nearly identical speeds, regardless of their distance from the central regions. Instead of the expected smooth decline in velocity that characterizes well-behaved gravitational systems, these cosmic whirlpools exhibited uniform rotation that defied every mathematical prediction derived from centuries of successful physics. Picture a carousel gone mad where children near the center somehow move at exactly the same speed as those riding the outer edge, creating a uniform angular motion that violates everything we understand about rotating mechanical systems. Or imagine a whirlpool where water near the drain moves no faster than liquid at the periphery creating a flat vortex that contradicts the fluid dynamics governing every natural spinning system we've ever studied. The mathematical equations describing galactic rotation should work flawlessly because they represent the same gravitational principles that successfully predict planetary orbits, satellite trajectories, and binary star interactions with remarkable precision. These formulas incorporate the inverse square law, which describes how gravitational force weakens with distance, combined with orbital mechanics that balance centripetal acceleration against gravitational attraction to maintain stable circular motion. When astronomers applied these trusted mathematical tools to galactic systems, they expected to find rotation curves that peaked near galactic centers, then declined smoothly toward the outer edges, mirroring the behavior observed in planetary systems throughout the universe. Instead, their calculations produced predictions that differ dramatically from observational reality, creating a crisis in fundamental physics that persists to this day. The implications extend far beyond astronomical curiosity, because flat rotation curves suggest that either our understanding of matter distribution within galaxies is catastrophically incomplete, or the gravitational laws that govern everything from falling apples to orbiting planets require radical modification when applied to cosmic scales. This breakdown in predictive capability represents more than a technical problem for specialists. It reveals that humanity's most successful scientific theories encounter fundamental limitations when confronted with the behavior of matter and energy across galactic distances. The stubborn refusal of galaxies to obey gravitational mathematics has forced scientists to contemplate possibilities that seemed unthinkable just decades ago. Either the universe contains vast quantities of invisible matter that somehow escape detection despite intensive searches, or gravity itself operates according to different rules depending on the scale at which we observe its effects. What happens when an isolated anomaly transforms into a universal pattern that challenges everything we thought we knew about cosmic architecture? Initially, astronomers hoped that Vera Rubin's flat rotation curve discovery might represent an unusual exception, perhaps a quirky characteristic of the specific galaxy she studied, Andromeda, or maybe an artifact of observational limitations that would disappear with improved measurements and better telescopic technology. However, as more sophisticated instruments became available and observational techniques grew increasingly precise, a disturbing pattern began emerging across the astronomical community. Galaxy after galaxy revealed the same mysterious flat rotation behavior, regardless of size, age, stellar composition, or location within the cosmic web. Small dwarf galaxies containing only a few billion stars exhibited the same uniform rotation patterns as massive spiral systems harboring hundreds of billions of stellar inhabitants. Ancient elliptical galaxies, whose stars formed when the universe was young, displayed rotation characteristics identical to active star-forming spirals, where stellar nurseries continue creating new suns from collapsing gas clouds. Low surface brightness galaxies, so faint they barely register on photographic plates, maintain the same constant velocity profiles as brilliant galactic beacons visible across billions of light-years. Even irregular galaxies lacking the elegant spiral structure of systems like our Milky Way demonstrated rotation curves that remained stubbornly flat despite their chaotic, asymmetrical matter distributions. The universality of this phenomenon became increasingly apparent as astronomers expanded their surveys from dozens to hundreds, then thousands of galactic systems spanning vast regions of observable space. Each new measurement confirmed the same unsettling conclusion. Flat rotation curves represented not an isolated mystery, but rather a fundamental characteristic of galactic behavior throughout the cosmos. This wasn't limited to galaxies within our local galactic neighborhood or restricted to particular cosmic environments. Instead, flat rotation appeared wherever astronomers possessed sufficient observational capability to measure stellar velocities within distant galactic systems. Massive galaxy clusters containing thousands of individual members all exhibited the same anomalous rotation patterns, while isolated galaxies drifting alone through cosmic voids demonstrated identical velocity profiles. Galaxies with prominent central bulges showed flat rotation curves, as did systems dominated by thin galactic disks with minimal central concentration. Metal-rich galaxies formed from gas enriched by previous generations of stellar evolution displayed the same rotation characteristics as metal-poor systems representing some of the earliest galactic formation episodes in cosmic history. The consistency of these observations across such diverse galactic populations gradually forced astronomers to confront an uncomfortable realization. This wasn't a problem that could be solved by finding special circumstances, unusual environments, or measurement errors that might explain away inconvenient data. Instead, flat rotation curves appeared to represent a fundamental aspect of galactic physics that somehow emerged from the basic laws governing matter, energy, and gravitational interaction on cosmic scales. As observational capabilities expanded to encompass galaxies at increasingly great distances, astronomers discovered that this mysterious rotation behavior persisted even in systems whose light had traveled billions of years to reach Earth, meaning flat rotation curves characterize galactic behavior throughout most of cosmic history. The magnitude of this discovery became clear as scientists recognized that their most successful theories, which accurately predicted everything from planetary orbits to satellite trajectories, encountered systematic failure when applied to galactic systems regardless of observational circumstances. This wasn't a subtle discrepancy that might be resolved through minor theoretical adjustments or improved measurement techniques. Rather, it represented a complete breakdown in our ability to predict galactic behavior using established gravitational physics. The problem's scale encompassed not just individual galaxies but extended throughout the observable universe, suggesting that either our understanding of matter distribution was fundamentally flawed, or gravitational theory itself required radical revision to accommodate cosmic reality. This gradual recognition that flat rotation curves represented a universal characteristic of galactic physics created a profound shift in astronomical thinking, transforming what initially appeared as an isolated observational puzzle into evidence for missing physics that operated on the largest scales in nature. The quiet persistence of this anomaly across all galactic types and cosmic environments suggested that humanity's most cherished physical theories might be incomplete in ways that previous generations of scientists could never have imagined, opening possibilities for discoveries that would reshape our understanding of cosmic evolution and the fundamental forces that govern universal structure. How do scientists respond when confronted with observations that threaten to overturn centuries of successful physics by proposing something that has never been detected? When faced with the universal puzzle of flat galactic rotation curves, the astronomical community's initial response followed a time-honored scientific tradition: preserve existing theoretical frameworks by proposing additional components rather than abandoning proven mathematical relationships that had guided human understanding for generations. The dark matter hypothesis emerged as an elegant solution that allowed physicists to maintain their faith in Newtonian mechanics while explaining the mysterious behavior of rotating galaxies through the presence of vast quantities of invisible material distributed throughout cosmic space. Picture yourself walking through a completely darkened room where you can hear footsteps, sense movement, and feel objects shifting around you, yet your eyes detect absolutely nothing in the surrounding blackness. You know something substantial exists within that space because of its effects on your environment, even though direct visual confirmation remains impossible despite your best efforts to illuminate the hidden contents. Similarly, astronomers reasoned that galaxies might contain enormous amounts of matter that somehow escape detection through conventional telescopic observations, while still exerting the gravitational influence necessary to explain rapid stellar rotation speeds. This invisible substance would need to surround visible galactic components like an enormous transparent cocoon, providing the additional gravitational binding force required to prevent fast-moving stars from escaping into intergalactic space. The mathematical beauty of this solution lay in its conservative nature. Instead of discarding Newton's gravitational equations or proposing exotic modifications to fundamental physics, scientists could simply add more matter to their galactic models until theoretical predictions matched observational reality. Think of rebalancing a wobbly table by adding weight to compensate for uneven leg lengths, rather than replacing the entire furniture piece with a completely different design. Dark matter allowed astronomers to preserve the mathematical tools that had successfully described planetary motion, satellite trajectories, and binary star interactions while extending their applicability to galactic scales through the inclusion of additional gravitational sources. The hypothesis suggested that ordinary matter, everything composed of protons, neutrons, and electrons that form stars, planets, gas clouds, and living organisms, represents only a small fraction of total cosmic material. Instead, the universe would be dominated by exotic particles that interact gravitationally with normal matter, but remain invisible to electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. These mysterious particles would neither emit light like stars, reflect illumination like planets, nor absorb radiation like interstellar dust clouds, making them essentially undetectable through traditional astronomical techniques, despite comprising the vast majority of cosmic mass. Computer simulations incorporating dark matter produced rotation curves that matched galactic observations with remarkable precision, suggesting that invisible halos containing roughly 5 times more mass than visible stellar components could account for the flat velocity profiles observed throughout the universe. The elegance of this explanation appealed to scientists because it required no fundamental changes to established physical laws, no exotic modifications to gravitational theory, and no abandonment of mathematical principles that had proven reliable across countless terrestrial and astronomical applications. Adding dark matter felt like a natural extension of scientific methodology, similar to how 19th century astronomers successfully predicted Neptune's existence by analysing unexplained perturbations in Uranus's orbital path. The conservative approach of preserving theoretical frameworks while invoking additional components had precedent throughout scientific history, from explaining chemical reactions through atomic theory to understanding stellar energy through nuclear fusion processes. Dark matter represented a sophisticated application of Occam's razor. Rather than proposing complex modifications to gravitational physics, scientists could explain galactic rotation through the simplest possible addition to cosmic inventory. The hypothesis also possessed predictive power because dark matter halos would influence galactic behavior in ways that extended beyond rotation curves, creating testable consequences for gravitational lensing, galaxy formation processes, and large-scale cosmic structure evolution. This invisible component would need to clump together through gravitational attraction during the early universe, providing scaffolding upon which normal matter could condense to form the first stars and galaxies billions of years ago. The dark matter solution felt reasonable and intellectually satisfying because it preserved humanity's most successful mathematical descriptions of nature while explaining mysterious observations through the discovery of previously unknown cosmic constituents, maintaining continuity with established scientific traditions rather than demanding revolutionary theoretical upheavals. What would cosmic architecture look like if we could somehow see the invisible scaffolding that supposedly holds galaxies together across billions of years? Advanced computer simulations have attempted to map this hypothetical dark matter, revealing a universe that bears little resemblance to the familiar cosmos of stars, planets, and glowing nebulae that populate our telescopic observations. These computational models suggest that every galaxy sits nestled within an enormous spherical halo of invisible particles extending far beyond the visible stellar disk, creating cosmic structures that dwarf the brilliant spiral arms and central bulges we admire in astronomical photographs. The scale of these proposed dark matter halos staggers the imagination, with some extending 10 times farther from galactic centers than the most distant observable stars, creating invisible spheres of influence that stretch across millions of light-years of apparently empty space. According to these simulations, dark matter doesn't distribute itself uniformly throughout cosmic space, but instead clumps together in complex hierarchical patterns, forming filamentary networks that connect galaxy clusters across vast distances, while leaving enormous voids where virtually no matter exists at all. The computational requirements for modelling such structures push modern supercomputers to their limits, tracking the gravitational interactions of billions of individual particles as they evolve over cosmic timescales spanning 13 billion years of universal history. Perhaps most startling is the sheer quantity of invisible matter that these models require to reproduce observed galactic rotation curves and large-scale cosmic structure formation. Dark matter must comprise approximately 85% of all material content in the universe, relegating familiar atomic matter to a minor constituent that barely influences cosmic evolution except through its ability to emit electromagnetic radiation. This means that stars, planets, gas clouds, dust particles, and every living organism throughout cosmic history represent less than 15% of total universal mass, making the visible cosmos essentially irrelevant to gravitational dynamics on large scales. The remaining 85% consists of exotic particles possessing properties unlike anything encountered in terrestrial physics laboratories or astronomical observations. These hypothetical particles must interact gravitationally with ordinary matter and with each other, yet remain completely transparent to electromagnetic radiation across all wavelengths, from radio waves through visible light to high-energy gamma rays. Unlike ordinary atoms that absorb, emit, and scatter photons through electronic transitions, dark matter particles neither glow like stars nor reflect illumination like planetary surfaces, making them essentially invisible despite their gravitational effects on surrounding material. Even stranger, dark matter particles rarely interact with each other through electromagnetic or strong nuclear forces, allowing enormous concentrations to pass through solid objects and even through each other without significant collision or energy loss. Picture trying to construct a building from materials that possess mass and weight but cannot be touched, seen, or manipulated through any known physical process except gravity. Dark matter would need to clump together slowly through gravitational attraction alone, without the electromagnetic interactions that allow ordinary matter to lose energy and collapse into compact structures like stars and planets. Computer simulations suggest that dark matter halos form through a complex process called hierarchical structure formation, where smaller clumps gradually merge together over cosmic time to create progressively larger concentrations of invisible material. These simulations predict that dark matter began clustering shortly after the Big Bang, when the universe was still hot and dense, providing gravitational wells into which ordinary matter could later fall to begin forming the first stars and galaxies. The invisible halos would have assembled first, creating a cosmic skeleton that guided subsequent galaxy formation processes throughout universal history. According to these models, visible galaxies represent merely the luminous tips of enormous invisible icebergs, with most galactic mass residing in extended dark matter halos that contain no stars, emit no light, and interact with ordinary matter only through gravitational forces. The profound implications of this picture suggest that humanity's entire astronomical heritage, from ancient constellation mapping to modern deep space photography, has captured only a tiny fraction of cosmic reality. If dark matter models prove correct, then our most spectacular astronomical images show less than 15% of actual cosmic structure, while the remaining 85% remains forever hidden from direct observation, despite dominating universal evolution and determining the ultimate fate of cosmic expansion. This invisible cosmos would dwarf human perception in ways that challenge our most basic assumptions about the nature of reality itself. How could the collision of two massive galaxy clusters become one of the most compelling pieces of evidence for invisible matter distributed throughout the cosmos? Located approximately 3.8 billion light-years from Earth, in the constellation Carina, an extraordinary cosmic event called the Bullet Cluster provided astronomers with what many considered definitive proof that dark matter exists as a separate physical component distinct from ordinary atomic material. This system represents the aftermath of a catastrophic collision between two enormous galaxy clusters, each containing hundreds of individual galaxies bound together by gravitational attraction, smashing into each other at speeds exceeding 10 million kilometers per hour in one of the most energetic events known to occur since the Big Bang itself. The collision created a natural laboratory where different components of cosmic matter behaved according to their unique physical properties, allowing scientists to observe how ordinary and dark matter respond differently to the extreme conditions generated during such violent encounters. When galaxy clusters collide at these tremendous velocities, their constituent galaxies typically pass through each other relatively unaffected, because the vast distances between individual stellar systems prevent direct impacts between stars or planetary systems. However, the enormous clouds of hot gas permeating each cluster interact very differently, creating spectacular shockwaves and drag forces that slow down the gaseous material as it encounters resistance from the opposing cluster's heated plasma. X-ray observations from NASA's Chandra Space Telescope revealed this hot gas as brilliant pink regions where temperatures reach hundreds of millions of degrees, marking the locations where ordinary matter experienced significant deceleration during the cluster collision. The gas clouds, which represent the majority of normal atomic matter within galaxy clusters, became separated from their original galactic hosts as electromagnetic and fluid dynamic forces caused them to lag behind during the high-speed encounter. Meanwhile, gravitational lensing observations provided a completely independent method for mapping the total mass distribution throughout the collision site, regardless of whether that mass consisted of ordinary atoms or exotic dark matter particles. This technique exploits Einstein's prediction that massive objects warp spacetime sufficiently to bend light rays passing nearby, creating distorted images of background galaxies located far beyond the cluster system. By carefully analysing these distortions, astronomers can reconstruct detailed maps showing where gravitational effects are strongest, thereby revealing the locations of all no matter within the system, whether visible or invisible. The gravitational lensing maps of the Bullet cluster showed two distinct concentrations of mass located precisely where the galaxies themselves appeared in optical photographs, but separated by significant distances from the hot gas clouds visible in X-ray images. This dramatic separation between the locations of maximum gravitational effect and the regions containing most ordinary matter provided smoking gun evidence that invisible dark matter had passed through the collision essentially unimpeded. While normal matter experienced substantial drag forces, the dark matter apparently accompanied the galaxies through the collision without interacting significantly with gas clouds, electromagnetic fields, or even with itself, behaving like ghostly material that responds only to gravitational attraction. Computer simulations of cluster collisions successfully reproduced the observed separation pattern only when they included substantial amounts of collisionless dark matter surrounding each galaxy within the merging systems. These models predicted that dark matter would continue moving at high speeds through the collision zone, while ordinary matter experienced deceleration through electromagnetic interactions, producing exactly the spatial offset between gravitational effects and visible matter observed in the Bullet cluster. The compelling nature of this evidence convinced many astronomers that dark matter represented physical reality rather than theoretical convenience, because alternative explanations requiring modifications to gravitational physics struggled to account for the clear separation between mass and ordinary matter revealed by this cosmic collision. The Bullet cluster seemed to demonstrate that dark matter possesses genuine physical existence independent of normal atoms, behaving according to its own dynamics while influencing cosmic evolution through gravitational forces alone. This natural experiment provided the kind of direct observational test that had been missing from earlier dark matter evidence, where rotation curves and gravitational lensing could potentially be explained through alternative theoretical approaches. The dramatic visual impact of seeing matter and mass separated across cosmic distances created widespread scientific conviction that invisible components dominate universal composition, transforming dark matter from speculative hypothesis into established astronomical fact within much of the research community. What happens when the most sophisticated scientific instruments ever built fail to detect the particles that supposedly comprise 85% of cosmic reality? For decades, experimental physicists have constructed increasingly elaborate detection systems designed to catch dark matter particles as they stream through Earth from the depths of space. Yet despite billions of dollars in funding and countless hours of patient observation, these efforts have produced nothing but empty results and mounting scientific frustration. Deep underground laboratories carved into mountainsides and buried beneath miles of solid rock shield ultra-sensitive detectors from cosmic radiation, creating pristine environments where researchers hope to observe the faint signals produced when hypothetical dark matter particles interact with specially designed target materials. These subterranean facilities, including installations in former mines throughout Europe, North America, and Asia, house detector arrays filled with liquid xenon, crystalline germanium, and other exotic substances chosen for their potential sensitivity to theoretical dark matter interactions. Scientists cool these materials to temperatures approaching absolute zero, eliminate electromagnetic interference through multiple layers of shielding, and monitor them continuously for years at a time, searching for the tiny energies deposits that would indicate dark matter particle collisions with atomic nuclei. The detectors themselves represent marvels of engineering precision, capable of measuring energy transfers smaller than those produced by individual photons of visible light, yet they consistently record only background noise from natural radioactivity and occasional cosmic ray interactions despite their extraordinary sensitivity. Particle accelerators at facilities like CERN have attempted to create dark matter particles through high-energy collisions between protons accelerated to nearly the speed of light, hoping to produce these elusive particles in controlled laboratory conditions where their properties might be studied directly. These experiments smash atomic nuclei together with energies exceeding those present during the first moments after the Big Bang, creating showers of exotic particles that exist for mere fractions of seconds before decaying into more stable forms. Sophisticated detector arrays surrounding the collision points track the paths and energies of thousands of particles produced during each impact, searching for missing energy that might indicate dark matter, particle creation, and escape from the experimental apparatus. Despite generating collision energies that dwarf anything achievable through natural processes on Earth, these accelerator experiments have failed to produce convincing evidence for dark matter particles, even though theoretical models predict they should be created readily under such extreme conditions. Space-based observatories orbiting high above Earth's protective atmosphere scan cosmic radiation for signatures of dark matter particle interactions or decay processes that might reveal their presence throughout the galaxy. These satellite experiments monitor gamma rays, cosmic ray spectra, and other forms of high-energy radiation streaming toward Earth from distant cosmic sources, looking for anomalous signals that could indicate dark matter annihilation events occurring within galactic halos or intergalactic space. Advanced spectrometers analyze the energy's distributions of cosmic particles with unprecedented precision, searching for characteristic peaks or absorption features that would betray the influence of dark matter interactions on cosmic radiation propagation. Despite decades of observations from multiple satellite missions equipped with progressively more sensitive instruments, these space-based searches have yielded no definitive detections of dark matter signatures, adding to the growing catalogue of negative experimental results. The technological sophistication of detection methods has increased exponentially over successive generations of experiments, with each new iteration offering improved sensitivity, reduced background noise, and enhanced discrimination between genuine signals and false positives. Modern detectors incorporate advances in cryogenic technology, quantum sensors, artificial intelligence algorithms for data analysis, and material science that would have seemed impossible just decades ago. Research groups coordinate their efforts internationally, sharing data and techniques to maximize detection efficiency while minimizing systematic errors that might obscure genuine dark matter signals. Yet despite these remarkable technological achievements and the dedicated efforts of thousands of skilled researchers worldwide, direct detection attempts have produced only upper limits on dark matter interaction rates rather than positive identification of particle properties. The persistent absence of experimental confirmation has created a peculiar situation where theoretical physicists continue refining models for particles that have never been directly observed, while experimentalists design ever more sensitive apparatus to search for phenomena that remain stubbornly elusive despite intensive investigation spanning multiple decades and consuming enormous scientific resources. When does a scientific hypothesis cross the line from elegant explanation to elaborate excuse-making that requires increasingly complex assumptions to maintain credibility? As decades of negative experimental results accumulated alongside mounting observational puzzles, some physicists began questioning whether dark matter had evolved from a simple solution into an unwieldy theoretical construction requiring constant modification to accommodate contradictory evidence. The original dark matter concept possessed appealing simplicity. Add invisible particles to galaxies and cosmic structure formation, problems disappear through additional gravitational attraction. However, reconciling dark matter models with diverse astronomical observations has demanded increasingly specific particle properties that seem tailored to solve individual problems rather than emerging from fundamental physical principles. Galaxy formation simulations require dark matter particles that interact weakly, enough to avoid detection, yet strongly enough to clump together during cosmic evolution. Cosmic microwave background observations demand specific thermal properties that differ from those needed to explain galactic rotation curves. Large-scale structure formation models work best with cold dark matter particles moving slowly compared to light, while explaining certain galactic phenomena seems to require warm or even hot dark matter components with completely different characteristics. The growing list of required properties has transformed dark matter from a simple hypothesis into a complex theoretical framework where particle characteristics must be carefully adjusted to match each new observational constraint. Critics argue that this fine-tuning process resembles the epicycles that ancient astronomers added to geocentric models when planetary observations failed to match theoretical predictions, creating increasingly complicated explanations rather than questioning fundamental assumptions. Different cosmic scales apparently require different dark matter behaviours. Galaxy clusters need particles that interact gravitationally, but pass through ordinary matter without significant collision, while galaxy formation demands particles capable of dissipating energy through some unknown mechanism to explain why galactic centres contain dense stellar concentrations rather than smooth dark matter distributions. Small-scale structure observations suggest dark matter should form numerous tiny halos throughout galactic neighbourhoods, yet astronomical surveys detect far fewer dwarf galaxies than these models predict, forcing theorists to invoke complex feedback mechanisms that somehow suppress star formation in most dark matter clumps. The Caucus problem illustrates another troubling inconsistency. Computer simulations consistently produce dark matter halos with dense central regions, while observational evidence suggests galactic centres contain much less concentrated mass distributions than models predict. Resolving this discrepancy requires additional physics beyond simple gravitational collapse, such as stellar feedback processes that somehow modify dark matter distributions through mechanisms that remain poorly understood. Furthermore, the missing satellite problem highlights the gap between theoretical predictions and observational reality. Dark matter simulations generate thousands of small satellite halos around massive galaxies like our Milky Way, yet we observe only a few dozen actual satellite galaxies, requiring elaborate explanations for why most dark matter clumps fail to form visible stellar systems. Each solution to these problems introduces new complications that must be reconciled with other observational constraints, creating a web of interdependent assumptions that grows more complex with every additional measurement. The situation has become uncomfortable for many physicists because explaining relatively straightforward astronomical observations now requires invoking multiple types of exotic particles with precisely calibrated properties that have no analogue in laboratory physics. Some researchers worry that dark matter models have become unfalsifiable because any contradictory observation can potentially be accommodated through adjustments to particle properties or the inclusion of additional physical processes. The philosophical question emerges: at what point does adding complexity to preserve a favoured theory become less scientifically productive than exploring alternative explanations that might require fewer assumptions? Whispers of dissent have grown louder as younger scientists, less invested in decades of dark matter research, begin exploring radical alternatives that seemed unthinkable when the invisible matter paradigm first gained acceptance. These researchers argue that the accumulation of problems requiring increasingly sophisticated solutions suggests something fundamental might be wrong with the dark matter approach itself. Perhaps the universe operates according to different physical principles than those underlying current theoretical frameworks, making invisible matter unnecessary if gravity behaves differently on cosmic scales than laboratory experiments suggest. The growing discomfort with dark matter's complexity has opened intellectual space for alternative ideas that seemed heretical just years ago, as scientists gradually recognize that the most elegant solutions sometimes require abandoning cherished assumptions rather than preserving them through ever more elaborate theoretical constructions. What profound philosophical implications arise when the scientific method encounters phenomena that seem fundamentally beyond experimental verification or direct observation? The persistent failure to detect dark matter particles despite decades of increasingly sophisticated searches has forced the scientific community to grapple with uncomfortable questions about the nature of knowledge, the limits of empirical investigation, and the wisdom of continuing massive investments in technologies designed to find something that may simply not exist. This situation creates a unique paradox in modern physics. How can researchers distinguish between particles that interact so weakly they remain perpetually beyond detection capabilities versus particles that don't exist at all? The philosophical challenge extends beyond mere technical limitations because dark matter theory predicts interaction rates so feeble that even perfect detectors might require centuries of observation to accumulate sufficient evidence for definitive conclusions. If theoretical models prove correct, dark matter particles streaming through underground laboratories would produce signals so rare that distinguishing genuine events from random background fluctuations becomes an exercise in statistical interpretation rather than clear experimental demonstration. This raises profound epistemological questions about what constitutes adequate scientific evidence and how long researchers should persist in searching for phenomena that remain stubbornly elusive despite enormous expenditures of time, money, and human intellectual resources. The history of science provides both encouraging and cautionary examples of invisible phenomena that eventually yielded to experimental scrutiny. Neutrinos required decades between theoretical prediction and successful detection, while luminiferous ether consumed scientific attention for generations before being abandoned as unnecessary for explaining electromagnetic wave propagation. Contemporary dark matter searches have already consumed more resources than most major scientific endeavours in human history, involving thousands of researchers across multiple continents working with budgets measured in billions of dollars. Yet unlike previous searches for elusive particles that eventually produced positive results, dark matter detection efforts have yielded only increasingly stringent upper limits on interaction probabilities rather than approaching actual discovery. The question naturally arises: at what point does scientific conservatism, which counsels patience and persistence in experimental programs, transform into counterproductive stubbornness that prevents exploration of revolutionary alternative explanations? Some researchers argue that continuing to refine detection technologies represents sound scientific methodology because breakthrough discoveries often require technological capabilities that exceed initial experimental attempts by orders of magnitude. Others contend that negative results over such extended periods suggest fundamental problems with the dark matter hypothesis itself, rather than merely indicating insufficient experimental sensitivity. This tension between conservative and revolutionary approaches reflects deeper disagreements about how science should respond when established theoretical frameworks encounter persistent observational challenges. The possibility that dark matter doesn't exist forces scientists to confront the humbling prospect that humanity's most sophisticated theoretical models might be fundamentally flawed despite their remarkable success in describing many cosmic phenomena. Accepting this possibility requires intellectual courage because it implies abandoning decades of research investment while embracing uncertainty about alternatives that might prove equally problematic. Yet clinging too tightly to failing paradigms has historically impeded scientific progress by discouraging exploration of radical new ideas that ultimately provided more accurate descriptions of natural phenomena. The transition toward considering alternative explanations need not invalidate the enormous effort invested in dark matter research, because those investigations have contributed invaluable knowledge about particle physics, detector technology, and cosmic structure formation regardless of their ultimate success in finding invisible matter. Negative experimental results possess scientific value by constraining theoretical possibilities and guiding future research jurisdictions, even when they fail to confirm initial hypotheses. The sophisticated underground laboratories, particle accelerators, and space-based observatories developed for dark matter searches have advanced human technological capabilities while generating unexpected discoveries in related fields ranging from material science to computer algorithms. Perhaps most importantly, the extended search for dark matter has demonstrated both the power and limitations of contemporary scientific methodology when confronting truly fundamental questions about cosmic composition and gravitational physics. Acknowledging the possibility that dark matter might not exist opens the intellectual space for exploring alternative approaches that seemed unthinkable during the height of invisible matter enthusiasm. These alternatives range from modifications to gravitational theory itself to exotic proposals involving emergent phenomena that arise from quantum mechanical effects operating across cosmic distances. Rather than representing failure, the inability to detect dark matter particles might signal an opportunity for revolutionary advances in physics that transcend current theoretical limitations, while providing more elegant explanations for mysterious astronomical observations that have puzzled researchers for generations. What if the solution to cosmic mysteries lies not in discovering new particles, but in recognizing that gravity itself operates differently than we assumed across the vast scales of galactic space? In 1983, Israeli physicist Mordechai Milgrom proposed a revolutionary alternative to dark matter that challenged fundamental assumptions about gravitational physics by suggesting that Newton's laws require modification when applied to systems experiencing extremely weak accelerations. Rather than invoking invisible matter to explain galactic rotation anomalies, Milgrom's modified Newtonian dynamics, known as MOND, proposed that gravitational attraction becomes enhanced at acceleration levels far below anything encountered in terrestrial laboratories or solar system environments. This radical departure from established physics suggested that the familiar inverse square law governing planetary orbits and falling objects represents only an approximation that breaks down when gravitational accelerations drop beneath a critical threshold approximately 10 billion times smaller than Earth's surface gravity. Milgram's insight emerged from careful analysis of galactic rotation curves, where he noticed that mysterious deviations from Newtonian predictions appeared precisely when stellar accelerations fell below this characteristic value, creating a natural boundary between classical gravitational behavior and modified dynamics. The elegance of MAND lies in its remarkable simplicity. Instead of requiring vast quantities of exotic particles with carefully tuned properties, the theory introduces just one additional parameter, an acceleration scale that marks the transition between standard and modified gravitational regimes. Below this critical acceleration, gravitational attraction no longer follows the familiar inverse square relationship, but instead decreases more slowly with distance, providing the additional force necessary to explain why galactic rotation curves remain flat rather than declining as Newtonian physics predicts. This single modification generates correct predictions for thousands of different galaxies without requiring individual adjustments or galaxy-specific parameters, suggesting that MOND captures something fundamental about gravitational physics rather than merely providing mathematical curve fitting to observational data. The theoretical framework predicts that when gravitational acceleration exceeds the critical threshold, familiar Newtonian dynamics emerge naturally, explaining why laboratory experiments and planetary observations conform perfectly to classical expectations, while galactic systems exhibit anomalous behavior. Computer simulations incorporating MOND successfully reproduce observed galactic rotation curves across diverse galaxy types, from massive spiral systems containing hundreds of billions of stars to tiny dwarf galaxies with stellar populations numbering in the millions. The theory also explains empirical relationships discovered by astronomers, such as the Tully-Fisher correlation linking galactic rotation speeds to stellar masses, which emerges naturally from MOND physics without requiring fine-tuning or additional assumptions. Perhaps most remarkably, MOND predicts the rotation curves of low-surface brightness galaxies, extremely faint systems where theoretical dark matter should completely dominate gravitational dynamics according to conventional models. These ghostly galaxies, barely visible even through powerful telescopes, exhibit rotation patterns that match MOND predictions precisely while presenting serious challenges for dark matter theories that struggle to explain why such diffuse systems maintain coherent structure across billions of years. The revolutionary implications extend far beyond galactic astronomy, because accepting MOND requires abandoning the assumption that gravitational physics remains constant across all scales and environments throughout the universe. If correct, Milgram's theory suggests that our most fundamental understanding of space, time, and gravitational interaction represents only a local approximation valid within solar system environments, but inadequate for describing cosmic phenomena across galactic and intergalactic distances. This possibility challenges the philosophical foundation of modern physics, which assumes that physical laws discovered through terrestrial experimentation apply universally throughout cosmic space and time. MOND implies that gravity might be an emergent phenomenon arising from more fundamental physics that manifests differently depending on the characteristic accelerations present within various cosmic environments. The theory's predictive success using a single parameter contrasts sharply with dark matter models that require multiple types of invisible particles with precisely calibrated properties to explain different astronomical observations. Milgram's approach exemplifies the scientific revolution in its purest form. Rather than adding complexity to preserve existing theoretical frameworks, MOND suggests that nature operates according to simpler principles than current physics recognizes. The profound implications of this alternative extend throughout theoretical physics, potentially connecting gravitational anomalies to quantum mechanical effects, thermodynamic principles, or exotic aspects of space-time geometry that remain poorly understood despite decades of intensive research by brilliant theoretical physicists worldwide. How can a single mathematical modification to gravitational theory successfully predict the behavior of thousands of completely different galactic systems without requiring any invisible matter whatsoever? The remarkable predictive power of modified Newtonian dynamics became apparent as astronomers tested Milgram's formula against increasingly diverse galactic observations, discovering that MOND's simple acceleration threshold could account for rotation curve anomalies across the entire spectrum of cosmic structures, from massive elliptical galaxies to the faintest dwarf systems barely visible through powerful telescopes. Unlike dark matter models that require careful adjustment of invisible halo properties for each individual galaxy, MOND employs the same fundamental acceleration scale to generate accurate predictions for spiral galaxies containing hundreds of billions of stars, irregular systems with chaotic morphologies, and ancient elliptical giants formed during the early epochs of cosmic history. This universality suggested that Milgram had identified something profound about gravitational physics, rather than merely creating another mathematical tool for fitting observational data to theoretical expectations. The theory's success became particularly evident when applied to low surface brightness galaxies, extremely diffuse stellar systems so faint they challenge the limits of astronomical detection capabilities yet maintain surprising structural coherence across billions of years of cosmic evolution. These ghostly galactic entities present severe problems for conventional dark matter theories because their visible stellar components contain insufficient mass to generate the gravitational binding necessary for long-term stability, requiring enormous invisible halos containing dozens of times more matter than observable stars and gas. However, MOND predicts the rotation curves of these enigmatic systems with extraordinary precision using only the visible stellar mass and gas content, eliminating the need for hypothetical dark matter components while explaining why such tenuous structures persist throughout cosmic time. Perhaps even more compelling, MOND naturally explains the famous Tully-Fisher relation, an empirical correlation discovered by astronomers that links galactic rotation velocities to total stellar masses in a remarkably tight relationship spanning 5 orders of magnitude in galactic properties. This relationship emerges directly from MOND's mathematical framework without requiring additional assumptions or parameter adjustments, suggesting that the acceleration threshold represents a fundamental aspect of cosmic physics rather than an arbitrary theoretical construction. Dark matter models struggle to reproduce this correlation because the relationship between visible stars and invisible halo masses depends on complex feedback processes during galaxy formation that remain poorly understood despite decades of intensive computer simulation efforts. The elegance of MOND's approach particularly appealed to physicists who valued theoretical parsimony and mathematical simplicity over the increasingly complex scenarios required by evolving dark matter paradigms. Rather than invoking multiple types of exotic particles with precisely calibrated interaction strengths, MOND achieved comparable or superior predictive accuracy through a single modification to familiar gravitational equations. This philosophical appeal resonated with scientists who remembered how previous theoretical breakthroughs had often simplified rather than complicated our understanding of natural phenomena, following the historical pattern established by Copernican astronomy, Newtonian mechanics, and Einstein's relativity theories. The theory's ability to make successful predictions across such diverse galactic environments using minimal assumptions suggested that nature might operate according to more elegant principles than contemporary dark matter research implied. Many physicists found MOND's conceptual clarity refreshing compared to the elaborate theoretical machinery required by invisible matter models, which demanded new particle physics beyond the standard model, exotic interaction mechanisms, and complex cosmological scenarios that seemed increasingly divorced from observational reality. MOND supporters argued that their approach embodied proper scientific methodology by proposing the minimum theoretical modification necessary to explain puzzling observations rather than constructing elaborate hypothetical frameworks based on undetected phenomena. The theory's predictive successes extended beyond individual galactic systems to encompass broader patterns in cosmic structure formation, including correlations between galactic properties and environmental factors that emerge naturally from MOND dynamics, but required careful fine-tuning within dark matter cosmologies. Computer simulations, incorporating modified gravitational physics, reproduced many observed characteristics of galactic populations without invoking invisible components, suggesting that MOND captured essential aspects of cosmic evolution overlooked by conventional approaches. These achievements convinced growing numbers of astronomers that alternative gravitational theories deserved serious consideration as potential solutions to cosmic puzzles that had resisted explanation through dark matter paradigms for several decades. The accumulating evidence supporting MOND's predictive capabilities created intellectual momentum for exploring radical departures from the established theoretical frameworks, encouraging scientists to question fundamental assumptions about gravitational physics that had remained unexamined since Newton's original formulation 3 centuries earlier. Why does a theory that works brilliantly for individual galaxies encounter serious difficulties when applied to larger cosmic structures and more extreme gravitational environments? Despite MOND's remarkable success in predicting galactic rotation curves and explaining various empirical relationships observed within stellar systems, the theory faces significant challenges that have prevented its widespread acceptance within the mainstream astronomical community. Galaxy clusters, those enormous assemblages containing thousands of individual galaxies bound together by gravitational attraction, present particularly troubling problems for modified gravitational dynamics because even MOND's enhanced gravitational effects cannot fully account for the binding forces necessary to maintain cluster coherence over cosmic timescales. Observations of cluster dynamics, including the velocities of individual member galaxies and the distribution of hot intracluster gas, consistently indicate total masses that exceed what visible matter plus MOND modifications can provide, forcing proponents to acknowledge that some additional invisible component remains necessary even within modified gravitational frameworks. This requirement undermines one of MOND's primary theoretical advantages over dark matter models, the elimination of hypothetical undetected particles from cosmological explanations. Large-scale structure formation presents another formidable obstacle, because MOND struggles to reproduce the cosmic web of filaments, voids, and superclusters observed throughout the universe without invoking additional physics beyond simple gravitational modifications. Computer simulations incorporating MOND dynamics fail to generate the complex hierarchical patterns of matter distribution that characterize our observable cosmos, particularly the formation of massive galaxy clusters during early cosmic epochs when the universe was much denser and hotter than today. The theory also encounters difficulties explaining the acoustic oscillations imprinted on the cosmic microwave background radiation, those subtle temperature fluctuations that provide crucial evidence about conditions during the universe's first few 100,000 years of existence. Gravitational lensing observations create additional complications because MOND predicts different mass distributions than those inferred from the bending of background galaxy images by intervening clusters and massive galaxies. While dark matter models can accommodate gravitational lensing measurements by adjusting invisible halo properties, MOND's predictions for lensing effects depend entirely on visible matter distributions and modified gravitational field strengths, leaving little flexibility for matching observed lens characteristics. The famous bullet cluster poses perhaps the most serious challenge for modified gravitational theories because the dramatic spatial separation between hot gas and gravitational lensing signals strongly suggests that invisible matter passed through the collision, while ordinary matter experienced significant deceleration through electromagnetic interactions. MOND proponents have proposed various mechanisms to explain this separation, including exotic forms of ordinary matter or additional gravitational effects, but these explanations require assumptions that compromise the theory's original simplicity and elegance. Furthermore, MOND faces fundamental theoretical problems because Milgram's original formulation operates entirely within Newtonian physics, making it incompatible with Einstein's general relativity and unable to address phenomena involving strong gravitational fields or high velocities. The development of relativistic extensions, particularly Jacob Bekenstein's tensor vector scalar theory known as TVS, attempted to resolve these limitations by embedding MOND behavior within a modified version of general relativity. However, TVS introduces additional fields and mathematical complexity that somewhat diminish the theoretical parsimony that originally made MOND appealing, while creating new problems in reconciling modified gravity with other aspects of fundamental physics. These relativistic versions struggle to explain gravitational wave propagation, cosmological expansion history, and various other phenomena that general relativity handles successfully, suggesting that constructing consistent modified gravitational theories requires more radical departures from established physics than initially anticipated. The accumulation of these problems has maintained skepticism within the mainstream physics community, where most researchers remain convinced that dark matter provides a more complete explanation for cosmic anomalies despite its own unresolved issues. Many physicists argue that while MOND captures important aspects of galactic dynamics, its failures on larger scales indicate fundamental limitations that prevent it from serving as a complete alternative to dark matter cosmology. The theory's inability to address all gravitational anomalies using a single consistent framework suggests that either additional modifications are necessary, or that different physical phenomena require different explanations, rather than being unified under a single theoretical umbrella. These ongoing challenges have relegated MOND to minority status within contemporary astrophysics, though recent observational developments continue generating interest in modified gravitational approaches among researchers seeking alternatives to increasingly complex dark matter scenarios. How do scientific communities become so deeply invested in competing explanations that objective evaluation becomes nearly impossible, transforming intellectual disagreements into passionate ideological battles? The confrontation between dark matter and a modified gravity represents far more than a technical dispute about galactic rotation curves or cosmic structure formation. It embodies a fundamental clash between radically different philosophical approaches to understanding physical reality and the proper methodology for advancing scientific knowledge. Dark matter advocates embrace a conservative strategy that preserves the mathematical framework of general relativity while expanding the cosmic inventory to include exotic particles that interact only gravitationally with ordinary matter. This approach follows established scientific tradition by maintaining theoretical continuity with proven physical laws while proposing new components to explain anomalous observations, much like 19th century astronomers successfully predicted Neptune's existence by analysing unexplained perturbations in Uranus's orbital motion. Proponents argue that adding invisible matter represents the minimum theoretical modification necessary to explain cosmic puzzles while preserving the remarkable mathematical edifice that has guided human understanding of gravity for over a century. Meanwhile, modified gravity enthusiasts champion a revolutionary perspective that questions whether our most fundamental assumptions about gravitational physics remain valid across all scales and environments throughout the universe. These researchers contend that nature might operate according to different principles than those discovered through terrestrial experimentation and solar system observations, suggesting that gravitational anomalies reveal new physics rather than requiring additional cosmic components. Their approach demands abandoning cherished theoretical frameworks in favor of mathematical relationships that seem alien compared to familiar Newtonian and Einsteinian formulations, yet potentially capture more accurate descriptions of cosmic behavior than existing paradigms. The philosophical divide extends beyond technical details to encompass broader questions about scientific methodology, the relationship between theory and observation, and the appropriate response when established frameworks encounter persistent anomalies. Dark matter researchers emphasize the importance of maintaining theoretical consistency with laboratory physics and the danger of abandoning successful mathematical formulations based on astronomical observations that might suffer from systematic errors or incomplete understanding. They point to the historical success of particle physics in discovering exotic components like neutrinos and quarks that were initially proposed to explain puzzling experimental results, arguing that dark matter represents a natural extension of this methodology to cosmic scales. Modified gravity advocates counter that scientific progress often requires revolutionary breaks with previous thinking, citing examples from Copernican astronomy, quantum mechanics, and Einstein's relativity, where fundamental advances emerged through radical departures from established wisdom rather than incremental additions to existing theories. They argue that clinging too tightly to familiar frameworks can impede recognition of deeper truths about natural phenomena, particularly when accumulating evidence suggests that current paradigms may be fundamentally inadequate. The sociological dynamics surrounding these competing approaches reveal how scientific communities develop emotional attachments to particular theoretical frameworks that transcend purely rational considerations. Researchers invest decades building careers around specific approaches, developing expertise in specialized techniques, and forming professional networks based on shared theoretical commitments that create powerful incentives for defending favored paradigms against alternative explanations. Graduate students learn to think within established frameworks. Postdoctoral researchers seek positions with groups pursuing particular approaches, and senior scientists build reputations based on contributions to specific theoretical programs, creating institutional momentum that resists paradigm shifts even when observational evidence becomes problematic. Conference presentations often resemble adversarial proceedings, where advocates for competing theories challenge each other's assumptions, methodologies, and interpretations rather than collaboratively seeking objective truth through dispassionate analysis. Journal reviewers frequently evaluate manuscripts based on their compatibility with prevailing theoretical preferences rather than purely on methodological rigor or observational significance, creating publication biases that can distort the apparent weight of evidence supporting different approaches. Research funding agencies tend to support established programs with proven track records rather than speculative alternatives that might revolutionize understanding but carry higher risks of failure, further entrenching dominant paradigms while discouraging exploration of radical possibilities. The passionate defense of competing worldviews reflects deeper human psychological tendencies to seek coherent explanations that provide intellectual comfort and professional identity rather than remaining perpetually open to fundamental uncertainty about the nature of reality. Both camps develop sophisticated arguments for why their approach represents superior scientific methodology, while characterizing opponents' positions as misguided or even unscientific, creating intellectual echo chambers that reinforce existing beliefs while minimizing exposure to contradictory evidence or alternative interpretations. What happens when cutting-edge astronomical observations begin revealing cosmic behavior that challenges both dark matter models and modified gravity theories in unexpected ways? Recent developments in galactic astronomy have produced intriguing evidence that complicates the already complex debate between competing explanations for gravitational anomalies, with 2024 studies suggesting that galaxy rotation curves remain flat across distances extending far beyond previous measurements, potentially reaching millions of light-years from galactic centers where no theoretical framework had predicted such persistent uniformity. These findings emerged from advanced gravitational lensing techniques that allow astronomers to probe galactic mass distributions at unprecedented scales, revealing that the mysterious forces responsible for flat rotation curves continue operating across cosmic distances where both dark matter halos and MOND modifications were expected to weaken significantly. Improved statistical analyses of massive galaxy databases containing tens of thousands of systems have uncovered subtle correlations between galactic properties that seem to favor modified gravitational explanations over invisible matter scenarios, particularly regarding relationships between stellar mass, rotation velocity, and environmental factors that emerge naturally from MOND dynamics, but require careful fine-tuning within dark matter frameworks. These large-scale surveys benefit from machine learning algorithms capable of identifying patterns across enormous datasets that would have been impossible to detect through traditional analytical methods, revealing empirical relationships that constrain theoretical models in ways that weren't feasible during earlier phases of this scientific debate. Perhaps most significantly, recent gravitational lensing measurements using space-based telescopes have achieved unprecedented precision in mapping mass distributions within galaxy clusters and individual galactic systems, producing results that don't align perfectly with either dark matter predictions or modified gravity expectations. The James Webb Space Telescope's exceptional infrared capabilities have enabled detailed observations of extremely distant galaxies whose light traveled billions of years to reach Earth, providing snapshots of cosmic conditions during earlier epochs when theoretical models make distinctly different predictions about galactic behavior and structure formation processes. These observations suggest that galactic rotation anomalies have persisted throughout most of cosmic history, constraining scenarios where dark matter properties or gravitational modifications might have evolved significantly since the early universe. However, the same data reveal complexities in galactic mass distributions that neither theoretical framework fully explains, including variations in rotation curve shapes that seem to correlate with galactic environment, stellar age populations, and morphological characteristics in ways that current models struggle to reproduce accurately. Advanced computer simulations incorporating both dark matter physics and modified gravitational dynamics continue revealing discrepancies between theoretical predictions and observational reality, suggesting that either additional physical processes remain unaccounted for, or that both approaches capture only partial aspects of more complete underlying phenomena. New statistical techniques for analysing cosmic microwave background radiation have identified subtle features that might constrain dark matter particle properties or provide evidence for modified gravitational effects during cosmic recombination. Though these signals remain at the edge of current detection capabilities and require confirmation through independent observational methods. Simultaneously, laboratory experiments searching for dark matter particles have achieved remarkable sensitivity improvements while continuing to yield negative results, pushing theoretical models toward increasingly exotic scenarios involving particles with interaction strengths so weak they might remain forever beyond experimental detection. Modified gravity researchers have developed sophisticated relativistic extensions that address some previous theoretical limitations while introducing new complications that require additional observational tests to evaluate their viability compared to dark matter alternatives. The emergence of gravitational wave astronomy has opened entirely new observational windows for testing both paradigms, because these ripples in spacetime propagate differently through cosmic environments containing invisible matter, versus regions where gravity itself operates according to modified principles. Recent analyses of gravitational wave signals from merging black holes and neutron stars have begun constraining some modified gravity theories, while providing indirect information about dark matter distributions in the vicinity of these extreme gravitational sources. Perhaps most intriguingly, several independent research groups have reported evidence for correlations between galactic rotation anomalies and quantum mechanical phenomena that might connect cosmic-scale gravitational behavior to fundamental physics operating at subatomic scales, suggesting that the solution to dark matter puzzles might require revolutionary advances in our understanding of quantum gravity, rather than merely discovering new particles or modifying classical gravitational equations. These developments indicate that the decades-long debate between dark matter and modified gravity approaches may be entering a new phase where both theoretical frameworks undergo significant modifications to accommodate observational complexities that neither originally anticipated, potentially leading toward hybrid explanations that incorporate elements from multiple competing paradigms. What profound truths about existence itself hang in the balance as humanity grapples with cosmic mysteries that challenge our most basic assumptions about the nature of reality? The stakes in this scientific debate extend far beyond technical questions about galactic rotation curves or particle detection experiments, because either resolution would fundamentally transform human understanding of our place within a universe that operates according to principles radically different from our everyday experience. If dark matter proves real, then visible reality represents merely the luminous tip of a cosmic iceberg where 85% of all substance remains forever beyond direct perception. Creating a universe dominated by invisible entities that shape galactic evolution, guide cosmic structure formation, and determine the ultimate fate of everything we can observe while remaining perpetually hidden from human senses. This scenario suggests that consciousness emerged within a cosmos where most fundamental constituents lie outside the reach of electromagnetic interaction, making the universe inherently mysterious in ways that transcend temporary limitations of current technology or experimental technique. The implications extend beyond astronomy to challenge basic assumptions about knowledge, perception, and the relationship between observable phenomena and underlying reality, raising questions about whether human understanding can ever encompass the full scope of cosmic architecture when most cosmic components remain fundamentally undetectable through any conceivable observational method. Alternatively, if modified gravity explanations prove correct, then humanity's most successful theoretical frameworks, mathematical relationships that have guided scientific progress for centuries and enabled remarkable technological achievements from space exploration to quantum electronics, represent merely provisional approximations that break down when applied beyond the limited environmental conditions where they were originally discovered and tested. This possibility suggests that gravitational physics itself operates according to scale-dependent principles that manifest differently across various cosmic environments, implying that the universe follows more complex mathematical rules than those encoded in textbooks and used for engineering applications throughout human civilization. The prospect that Newton's and Einstein's theories require fundamental modification challenges scientific methodology itself, because these frameworks have proven so successful within their domains of applicability that questioning their universal validity seemed unthinkable until astronomical observations forced such considerations. Either resolution implies that human perception and scientific capability have evolved within a cosmic context that systematically conceals its true nature, whether through the invisibility of dominant matter components or through the limitation of gravitational theory to local environmental conditions that represent tiny fractions of cosmic parameter space. The philosophical discomfort arising from these possibilities reflects deeper human psychological needs for coherent explanations that provide intellectual security and predictive power over natural phenomena. Yet both dark matter and modified gravity scenarios suggest that the universe operates according to principles that transcend human cognitive evolution and observational capabilities. Perhaps most unsettling, both possibilities imply that scientific knowledge remains fundamentally incomplete despite centuries of remarkable progress in understanding natural phenomena, suggesting that future discoveries might reveal additional layers of cosmic complexity that current theoretical frameworks cannot anticipate or accommodate. The comfort traditionally derived from scientific explanations depends partly on their ability to provide definitive answers that resolve uncertainty through precise mathematical descriptions of natural behavior. Yet the dark matter versus modified gravity debate has persisted for decades without clear resolution, despite enormous experimental and theoretical efforts by brilliant researchers worldwide. This situation forces recognition that some cosmic questions might require generations or centuries to answer definitively, demanding intellectual humility about the limitations of contemporary scientific capability, while maintaining confidence in methodological approaches that have proven successful within more restricted domains. The cosmic perspective emerging from either scenario fundamentally alters humanity's relationship with the universe by revealing that our species developed consciousness and scientific capability within a reality whose essential characteristics remain hidden, whether through invisible matter that dominates cosmic evolution or through gravitational physics that operates differently across scales beyond direct human experience. These possibilities suggest that existence itself unfolds within contexts far more mysterious and complex than everyday experience suggests, challenging anthropocentric assumptions about cosmic comprehensibility, while inspiring awe at the vast scales and exotic phenomena that characterize universal architecture. The recognition that either dark matter or modified gravity represents cosmic reality implies that human knowledge represents early stages in a potentially endless quest to understand phenomena that transcend the environmental conditions under which consciousness and scientific methodology originally evolved, opening perspectives on cosmic mystery that simultaneously humble human pretensions while inspiring continued exploration of natural phenomena that exceed current theoretical frameworks and observational capabilities. How could the discovery that cosmic expansion is accelerating rather than slowing down reveal yet another fundamental gap in humanity's understanding of gravitational physics across universal scales? In the late 1990s, two independent teams of astronomers studying distant supernovae made a startling observation that would revolutionize cosmology by demonstrating that the universe's expansion rate has been increasing over the past several billion years, directly contradicting theoretical expectations based on general relativity and known forms of matter and energy. These Type Ia supernovae, stellar explosions so consistent in their brightness that they serve as cosmic lighthouses for measuring distances across billions of light years, appeared significantly dimmer than predicted by models assuming that gravitational attraction should gradually decelerate cosmic expansion following the Big Bang. The unexpected faintness of these stellar beacons indicated that they were farther away than anticipated, implying that space itself has been stretching at an accelerating pace that requires some mysterious repulsive force to overcome the attractive gravitational influence of all cosmic matter. This discovery introduced yet another invisible component to the cosmic inventory: dark energy, a hypothetical form of energy density that permeates all of space and exerts negative pressure capable of driving accelerated expansion against the attractive pull of ordinary and dark matter combined. Unlike dark matter, which clumps together to form galactic halos and cosmic structure, dark energy appears uniformly distributed throughout empty space, contributing approximately 70% of the universe's total energy density while remaining completely undetectable through any direct observational method. When combined with the 85% of matter that supposedly consists of invisible dark matter particles, these discoveries revealed that approximately 95% of cosmic reality consists of components that have never been directly observed, detected in laboratory experiments, or explained through established physical theories. This staggering realization suggests that human scientific understanding encompasses only a tiny fraction of cosmic phenomena, reducing all familiar matter and energy, including stars, planets, galaxies, radiation, and living organisms, to minor constituents within a universe dominated by completely mysterious entities. The conceptual challenges posed by dark energy exceed even those associated with dark matter, because this component must somehow maintain constant energy density as space expands, creating new dark energy out of nothing to fill the increasing volume while preserving its uniform distribution throughout cosmic space. No known physical mechanism can account for such behavior, because conservation of energy, one of the most fundamental principles in physics, forbids the spontaneous creation of energy from empty vacuum. Yet dark energy models require precisely this impossible process to explain accelerating cosmic expansion. Furthermore, theoretical attempts to identify dark energy with quantum vacuum fluctuations produce energy densities that exceed observational constraints by factors of 10 to the power of 120, representing perhaps the most spectacular failure of theoretical prediction in scientific history. The simultaneous existence of both dark matter and dark energy problems suggests that gravitational physics encounters systematic difficulties when applied to cosmic scales far beyond the solar system environments where general relativity has proven remarkably successful. These failures span multiple independent phenomena, including galactic rotation curves, galaxy cluster dynamics, gravitational lensing observations, cosmic structure formation, and universal expansion history, creating a pattern of anomalies that challenges confidence in current theoretical frameworks. The accumulating evidence suggests that either the universe contains vast quantities of exotic matter and energy forms that somehow escape detection despite intensive searches, or that gravitational theory itself requires fundamental modifications to accommodate cosmic-scale phenomena that weren't anticipated when Einstein developed general relativity over a century ago. Some researchers have begun exploring connections between dark matter and dark energy problems, investigating whether both phenomena might arise from common underlying physics involving modifications to gravitational dynamics or exotic quantum effects that manifest differently across various cosmic scales and environments. The possibility that these apparently distinct mysteries share common explanations has inspired theoretical approaches that attempt to unify dark sector physics through single theoretical frameworks capable of explaining both galactic rotation anomalies and accelerating cosmic expansion without invoking multiple types of invisible components. However, these unified approaches face enormous challenges in reproducing the detailed observational characteristics of both phenomena while maintaining consistency with established physics in regimes where current theories work successfully. The growing recognition that fundamental physics appears incomplete at cosmic scales has created unprecedented uncertainty about the basic nature of reality itself, forcing scientists to confront the possibility that centuries of theoretical progress have captured only local approximations to more complex universal principles that operate beyond current human comprehension. What drives theoretical physicists to develop increasingly exotic gravitational theories that challenge centuries of established mathematical frameworks in their desperate search for cosmic understanding? The persistent failures of both dark matter detection efforts and standard gravitational physics to explain cosmic anomalies have sparked an explosion of alternative theoretical approaches that reimagine gravity itself as something far more complex and scale-dependent than Newton or Einstein ever anticipated. Among the most promising candidates, SFR, gravity modifies the mathematical structure of general relativity by replacing Einstein's simple curvature term with arbitrary functions of space-time curvature, allowing gravitational dynamics to behave differently across various cosmic environments without requiring invisible matter components. These theories suggest that the fundamental action describing gravitational physics involves higher-order curvature terms that become significant only when applied to galactic and cosmological scales, naturally producing modified dynamics that could account for both dark matter and dark energy phenomena through purely geometrical effects. Emergent gravity represents an even more radical departure from conventional thinking by proposing that gravitational attraction itself arises from more fundamental quantum mechanical processes operating at microscopic scales, similar to how thermodynamic properties like temperature and pressure emerge from statistical behavior of molecular constituents without being fundamental forces in their own right. These approaches draw inspiration from holographic principles in string theory, suggesting that gravity might be an emergent phenomenon arising from quantum entanglement and information theory operating on the boundaries of cosmic regions rather than representing a fundamental force that acts discretely between massive objects. Holographic theories propose that all gravitational information within any cosmic volume can be encoded on two-dimensional surfaces surrounding that region, implying that three-dimensional space itself might be an emergent illusion arising from more fundamental physics operating in lower dimensions. Such radical reconceptualizations of space-time geometry and gravitational physics open possibilities for explaining cosmic anomalies without invoking invisible matter or energy components, instead suggesting that apparent dark sector phenomena reflect limitations in current understanding of how quantum mechanics and gravity combine to produce macroscopic gravitational effects. Thermodynamic approaches to gravity explore connections between gravitational physics and entropy, building on Stephen Hawking's discovery that black holes possess temperature and entropy proportional to their surface areas rather than their volumes. These theories suggest that gravitational dynamics might emerge from underlying thermodynamic processes involving information storage and processing on cosmic scales, potentially explaining why gravitational behavior becomes modified in regimes where quantum effects and thermodynamic considerations become cosmologically relevant. Some researchers investigate whether the apparent acceleration of cosmic expansion and galactic rotation anomalies reflect entropy production processes occurring throughout cosmic space, creating effective negative pressure and enhanced gravitational attraction through mechanisms that remain invisible to conventional observational methods. The proliferation of alternative gravitational theories reflects growing recognition that standard approaches have reached theoretical dead ends, where additional progress requires abandoning fundamental assumptions about the nature of space-time and matter and energy that have guided physics for centuries. Rather than continuing to search for increasingly exotic particles or invoke ever more complex invisible matter scenarios, many theorists now explore whether gravity itself operates according to principles that transcend current mathematical formulations and conceptual frameworks. These explorations encompass ideas ranging from extra-dimensional theories where gravity becomes diluted by leaking into higher dimensional spaces, to discrete space-time models where continuous geometry represents only an approximation to more fundamental pixelated structures operating at Planck-scale distances. Quantum gravity approaches attempt to unify general relativity with quantum mechanics through frameworks like loop quantum gravity, causal dynamical triangulation, and emergent space-time theories that suggest gravitational physics requires complete reformulation when quantum effects become significant on cosmic scales. The expanding toolkit of theoretical possibilities reflects both the intellectual freedom that comes from recognizing the inadequacy of current paradigms and the practical necessity of exploring radical alternatives when conventional approaches consistently fail to explain fundamental cosmic phenomena. This theoretical proliferation has created unprecedented diversity in gravitational physics research, with different groups pursuing completely incompatible approaches that make dramatically different predictions about cosmic evolution, fundamental forces, and the ultimate nature of reality itself. The motivation for this theoretical explosion stems from mounting evidence that the universe operates according to principles that exceed current human understanding in profound ways, requiring either the discovery of vast amounts of invisible matter and energy, or complete revisions to gravitational theory that acknowledge its limitations when applied beyond the local cosmic environments where it was originally developed and tested through solar system observations and laboratory experiments. How might the deepest unsolved problem in theoretical physics hold the key to understanding why our gravitational equations fail so spectacularly when applied to cosmic scales beyond our solar neighborhood? The persistent separation between general relativity and quantum mechanics represents perhaps the most fundamental challenge in modern physics, creating a conceptual chasm where our two most successful theoretical frameworks remain stubbornly incompatible despite decades of brilliant theoretical work aimed at unifying them into a single consistent mathematical description of nature. General relativity treats spacetime as a smooth, continuous geometric manifold, where matter and energy curve the fabric of reality according to Einstein's field equations, while quantum mechanics describes reality as fundamentally discrete, probabilistic, and governed by uncertainty principles that prevent simultaneous precise knowledge of complementary physical properties. This incompatibility becomes particularly problematic when attempting to understand gravitational phenomena occurring in extreme environments where both quantum effects and strong gravitational fields operate simultaneously, such as the interiors of black holes, the first moments following the Big Bang, or potentially within the mysterious cosmic structures that seem to require dark matter for theoretical consistency. Recent theoretical developments suggest that gravity itself might emerge from more fundamental quantum mechanical processes operating at microscopic scales, similar to how fluid dynamics emerges from molecular behavior without being encoded directly in the fundamental laws governing individual atoms or molecules. These emergent gravity theories propose that gravitational attraction represents a collective quantum phenomenon that arises when enormous numbers of quantum fields interact across cosmic distances, producing macroscopic effects that appear as classical gravitational forces but actually reflect underlying quantum entanglement networks spanning galactic and intergalactic space. If such theories prove correct, then the apparent failure of classical gravitational equations at cosmic scales might simply reflect limitations inherent in treating gravity as a fundamental force, rather than recognizing it as an emergent property of more basic quantum phenomena that operate according to different mathematical principles. Loop quantum gravity and related approaches suggest that spacetime itself possesses discrete, granular structure at the Planck scale, where distances become so small that quantum uncertainty relations prevent classical geometric concepts from maintaining their usual meaning. These theories predict that continuous spacetime represents only an approximation that breaks down when gravitational effects become sufficiently strong, or when examined across sufficiently large cosmic volumes where quantum corrections accumulate to produce macroscopically observable deviations from classical behavior. Such quantum modifications to gravitational dynamics could potentially explain galactic rotation anomalies, cosmic acceleration, and other dark sector phenomena, without requiring invisible matter or energy components, instead suggesting that these mysteries reflect quantum gravitational effects that become significant only when integrated across galactic and cosmological scales. Holographic principles derived from string theory and black hole thermodynamics suggest even more radical possibilities where three-dimensional space itself emerges from information processing occurring on two-dimensional boundary surfaces, implying that apparent cosmic volumes contain only the information that can be encoded on their surrounding boundaries. These holographic theories propose that dark matter phenomena might reflect information storage and retrieval processes operating on cosmic horizons rather than indicating the presence of additional material particles within galactic volumes, offering completely novel explanations for gravitational anomalies that transcend conventional particle physics approaches. The connection between quantum mechanics and cosmic-scale gravitational behavior becomes particularly intriguing when considering that quantum field theory predicts vacuum fluctuations throughout empty space that should contribute to gravitational dynamics through their energy density, yet attempts to calculate these contributions produce results that exceed observational constraints by enormous factors. Some researchers speculate that properly accounting for quantum vacuum effects might require mathematical techniques that haven't been developed yet, potentially revealing connections between microscopic quantum phenomena and macroscopic cosmic acceleration that current theoretical methods cannot capture accurately. Furthermore, the measurement problem in quantum mechanics, which concerns how quantum superposition states collapse into definite classical outcomes, might be related to gravitational effects in ways that become cosmologically significant when considered across galactic scales and cosmic time periods. These interconnections suggest that the dark matter and dark energy puzzles might not represent separate mysteries requiring independent explanations, but rather different manifestations of incomplete understanding regarding how quantum mechanics and gravity combine to produce cosmic-scale phenomena that appear anomalous or anomalous when analysed using classical gravitational theory. The possibility that quantum gravity holds solutions to cosmic mysteries creates unprecedented opportunities for theoretical unification where resolving fundamental problems in physics might simultaneously explain astronomical observations that have puzzled scientists for decades while revealing deeper connections between microscopic and macroscopic aspects of natural phenomena than previous generations of researchers could have imagined. Why might humanity's greatest cosmic puzzles represent sources of profound comfort rather than intellectual frustration? offering windows into the endless mystery that makes existence itself so remarkably beautiful. The persistent enigma surrounding gravity's apparent failures at cosmic scales provides something precious that definitive answers might actually diminish. An ongoing invitation to participate in the universe's deepest mysteries while maintaining humility about the limitations of human knowledge and the vast expanses of reality that remain beyond current comprehension. Throughout scientific history, the most transformative discoveries have emerged not from resolving simple technical questions, but from grappling with fundamental puzzles that seemed completely intractable for decades or centuries before breakthrough insights revealed previously unimaginable aspects of natural phenomena. The wave-particle duality of light perplexed physicists for generations before quantum mechanics provided mathematical frameworks that embraced, rather than eliminated, this apparent contradiction, suggesting that nature operates according to principles more subtle and complex than human intuition readily grasps. Similarly, the relationship between electricity and magnetism remained mysterious for centuries until Maxwell's equations revealed their deep unity through mathematical relationships that transformed both theoretical understanding and practical technology in ways that previous generations could never have anticipated. Continental drift theory faced decades of ridicule and dismissal before plate tectonics provided geological mechanisms that explained how continents could move across Earth's surface, revolutionizing understanding of planetary evolution while validating observations that had seemed impossible within earlier theoretical frameworks. These historical precedents suggest that our current gravitational puzzles might represent early stages in scientific revolutions that will eventually transform human understanding of space, time, matter, and energy in directions that contemporary physics cannot yet imagine. The beauty of living with cosmic uncertainty lies in recognizing that each unanswered question opens pathways toward discoveries that could reshape civilization's relationship with the universe, while revealing connections between phenomena that currently seem completely unrelated. Dark matter and modified gravity debates force researchers to question fundamental assumptions about reality itself, creating intellectual freedom to explore radical possibilities that might otherwise be dismissed as too speculative or revolutionary for serious consideration. This uncertainty drives creativity because scientists must develop entirely new conceptual tools, mathematical techniques, and experimental methods to address problems that exceed the scope of existing theoretical frameworks. The process of wrestling with seemingly impossible questions generates insights that often prove valuable in completely unexpected contexts, similar to how research into abstract mathematical concepts frequently discovers practical applications decades after their original development. Perhaps most importantly, cosmic mysteries maintain human connection to wonder and awe that easily disappears when scientific explanations become too complete or familiar, preserving space for imagination and curiosity that represents essential aspects of human consciousness and cultural development. The patience required for fundamental scientific breakthroughs operates on timescales that exceed individual human lifespans, demanding intellectual humility that acknowledges current knowledge as provisional while maintaining confidence in methodological approaches that have proven successful across centuries of scientific progress. Galileo's telescopic observations challenged geocentric cosmology, but required generations of additional work before Newton provided mathematical frameworks capable of explaining planetary motion through universal gravitational principles. Darwin's evolutionary insights sparked decades of controversy and research before genetic mechanisms revealed molecular foundations for biological inheritance and species transformation that validated his original theoretical vision while extending it far beyond anything he could have imagined. Einstein's relativity theories predicted gravitational waves whose detection required nearly a century of technological development before LIGO experiments confirmed these ripples in spacetime, using instruments sensitive enough to measure distortions smaller than 1,000th the diameter of a proton. These examples demonstrate that revolutionary scientific advances often require multiple generations of patient theoretical development combined with technological progress that gradually enables experimental tests of previously untestable predictions. Finding peace with incomplete understanding requires recognizing that uncertainty represents a natural and healthy state for human knowledge rather than indicating failure or inadequacy in scientific methodology, while acknowledging that some questions might require centuries or millennia before definitive resolution becomes possible through advances in both theoretical insight and observational capability. The cosmic mysteries surrounding gravity's behaviour connect contemporary researchers to the long historical tradition of scientists who pursued understanding, despite knowing their individual efforts might represent only small contributions toward eventual breakthroughs that would emerge through collective human intellectual endeavour spanning many generations. This perspective transforms current gravitational puzzles from sources of frustration into invitations for participation in humanity's ongoing conversation with the universe, where each new observation and theoretical insight adds pieces to conceptual puzzles whose complete solutions might ultimately reveal aspects of reality more beautiful and surprising than anything current imagination can anticipate. What extraordinary discoveries might emerge from the revolutionary astronomical instruments and experimental facilities that are beginning to peer deeper into cosmic mysteries than humanity has ever been able to explore before? The next decade promises unprecedented opportunities for resolving gravitational anomalies through technological capabilities that surpass current observational limits by orders of magnitude, potentially providing definitive evidence for dark matter particles, confirming modified gravity theories, or revealing completely unexpected phenomena that transcend both competing explanations. The James Webb Space Telescope has already begun capturing infrared observations of distant galaxies, whose light carries information about cosmic conditions during epochs when theoretical models make distinctly different predictions about structure formation, galactic evolution, and gravitational behavior across cosmic time. Future space-based observatories, including the Nancy Grace Roman Space Telescope and proposed successors, will survey millions of galaxies with precision sufficient to detect subtle correlations between galactic properties and environmental factors that could distinguish between dark matter and modified gravity scenarios through statistical analyses impossible with current datasets. Ground-based facilities like the Extremely Large Telescope and 30-meter telescope will achieve angular resolution approaching theoretical limits imposed by atmospheric turbulence, enabling detailed studies of individual stellar motions within distant galaxies while mapping gravitational effects across cosmic scales where competing theories diverge most dramatically. These massive instruments will work in concert with gravitational wave observatories including Advanced LIGO detectors, Virgo, and the proposed Einstein telescope to monitor space-time ripples produced by cosmic collisions that could reveal whether gravity propagates according to Einstein's predictions or follows modified dynamics that leave distinctive signatures in gravitational wave signals. Simultaneously, underground dark matter detection experiments are approaching sensitivity thresholds where theoretical models predict definitive results within the next decade, using liquid xenon detectors containing tens of tons of target material shielded from background radiation by kilometers of rock and sophisticated cryogenic systems that could finally capture direct evidence of invisible particles streaming through Earth from galactic halos. Next-generation particle accelerators, including proposed upgrades to the Large Hadron Collider and entirely new facilities designed specifically for dark matter searches, will explore energy regimes where exotic particles might be created artificially through high-energy collisions, providing laboratory confirmation of theoretical predictions about invisible matter properties. Advanced computer simulations powered by exascale computing architectures and artificial intelligence algorithms will model cosmic evolution with unprecedented detail, tracking billions of particles across cosmic time, while incorporating both quantum mechanical effects and general relativistic corrections that current simulations cannot accommodate simultaneously. Machine learning techniques applied to astronomical surveys containing billions of galactic observations will identify patterns invisible to human analysis, potentially revealing empirical relationships that constrain theoretical models in ways that haven't been anticipated by current research programs. These computational approaches might discover correlations between dark matter signatures and environmental factors across cosmic scales, or alternatively identify evidence supporting modified gravity through statistical patterns that emerge only when analyzing enormous datasets spanning diverse cosmic environments and evolutionary stages. The convergence of multiple independent observational methods creates unprecedented opportunities for cross-validation where different experimental approaches must yield consistent results if any particular theoretical framework accurately describes cosmic reality. Gravitational lensing observations from space-based telescopes, rotation curve measurements from ground-based spectroscopy, particle detection experiments in underground laboratories, and gravitational wave signals from cosmic collisions will provide complementary information about the same underlying physics, creating a comprehensive observational network capable of distinguishing between competing explanations with confidence levels impossible to achieve through individual experimental programs. Perhaps most intriguingly, the possibility remains that future discoveries will reveal phenomena that transcend both dark matter and modified gravity frameworks, potentially uncovering connections between quantum mechanics and cosmic-scale gravitational effects that require entirely new theoretical foundations. Recent theoretical work on emergent spacetime, holographic principles, and quantum gravity suggests that cosmic anomalies might reflect fundamental aspects of reality that current physics cannot accommodate, opening possibilities for revolutionary advances that would transform human understanding of space-time, matter, and energy in ways comparable to the quantum mechanical and relativistic revolutions of the early 20th century. The excitement of living through such a potential paradigm shift lies in recognizing that each new observation could provide the crucial piece of evidence that tips the scientific consensus toward one explanation or another, or alternatively reveals that the universe operates according to principles more beautiful and surprising than anything current theoretical frameworks have imagined. This moment in scientific history offers rare opportunities to witness the resolution of mysteries that have puzzled humanity for decades while participating in discoveries that might reshape civilization's cosmic perspective for generations to come. How does this invisible force that guides your every movement, from the gentle settling of your body into rest to the cosmic dance of galaxies across billions of light years, somehow contain within its familiar embrace the most profound mysteries about the nature of reality itself? Throughout our patient journey from Newton's falling apple to the edge of observable space, we've encountered a remarkable paradox where gravitational physics displays perfect mathematical elegance when applied to planetary orbits, satellite trajectories, and everyday terrestrial phenomena, yet encounters systematic failure when extended to the vast cosmic structures that define universal architecture. This strange duality reveals something beautiful about the relationship between human understanding and cosmic reality. The same force that feels so immediate and comprehensible in our daily experience somehow conceals secrets that challenge our most fundamental assumptions about space, time, matter, and the mathematical principles governing natural phenomena. The poetry emerges from recognizing that gravity operates as a bridge, connecting the intimate scale of human consciousness with the grandest cosmic processes, yet this bridge reveals gaps in our knowledge that grow more pronounced as we venture farther from the comfortable domain where our equations were originally discovered and tested. Each step outward from familiar territory has unveiled new layers of mystery, from Zwicky's fast-moving galaxy clusters through Rubin's flat rotation curves to the accelerating expansion that suggests most of the universe consists of completely unknown forms of matter and energy. These discoveries follow a pattern where gravitational anomalies appear precisely at the boundaries where human observational capability pushes beyond the environmental conditions that originally shaped our theoretical understanding, suggesting that gravity might be teaching us something profound about the limitations of knowledge derived from local experience. Whether the resolution involves invisible matter, comprising the vast majority of cosmic reality, or fundamental modifications to gravitational theory itself, either possibility implies that the universe operates according to principles far more subtle and complex than everyday experience suggests. The dark matter scenario would mean that consciousness emerged within a cosmos where most substance remains forever beyond direct perception, while modified gravity alternatives suggest that the mathematical relationships governing planetary motion represent only approximations to deeper physical laws that manifest differently across various cosmic scales and environments. Both possibilities connect us to wonder by revealing that the most familiar aspects of physical reality conceal the deepest mysteries about existence itself, transforming gravity from a solved problem into an ongoing invitation for intellectual exploration and spiritual contemplation. The gentle irony lies in recognizing that the force responsible for creating stable conditions necessary for life, consciousness, and scientific discovery simultaneously presents the greatest challenges to understanding the cosmic context within which these phenomena have emerged. Perhaps this mystery serves an essential purpose by maintaining appropriate humility about human knowledge while preserving space for continued discovery and theoretical development that might eventually reveal connections between gravitational physics and other fundamental aspects of reality, including quantum mechanics, thermodynamics, and information theory. The journey through gravitational anomalies also illuminates something beautiful about scientific methodology itself, demonstrating how patient observation and mathematical analysis can reveal cosmic phenomena that exceed the scope of direct human experience while acknowledging the provisional nature of theoretical understanding. Our exploration has shown how competing explanations can coexist for decades while researchers develop increasingly sophisticated experimental techniques and theoretical frameworks capable of distinguishing between alternative possibilities, creating intellectual tension that drives scientific progress while maintaining healthy skepticism about premature conclusions. The cosmic perspective emerging from gravitational mysteries connects individual human experience with the largest scales of space and time, revealing that the same physical principles governing personal movement through daily life also shape galactic evolution, cosmic structure formation, and universal expansion across billions of years of cosmic history. This connection suggests that understanding gravity more completely might provide insights into fundamental questions about consciousness, complexity, and the emergence of organization within cosmic systems that evolve from simple initial conditions toward the intricate structures that characterize contemporary universal architecture. As we conclude this gentle exploration through gravity's paradoxes, the invitation remains open for continued wonder about how this most intimate of forces somehow holds keys to unlocking cosmic secrets that exceed current human comprehension, while connecting each moment of personal experience with the vast, mysterious processes that govern galactic motion, cosmic acceleration, and the ultimate fate of everything we can observe throughout the endless depths of space and time.